All right, welcome everyone. So far we've discussed what an inverse matrix is, how we can find the inverse of an elementary matrix where just one row operation is being applied. And then we've talked about how we can find the inverse of a product of matrices. Namely, if I have the product of matrix of three, say, invertible matrices, then to take their inverse, we take the product of the inverse matrices in the opposite order. So it's kind of the equivalent of we want to do the reverse operations in the reverse order to get the inverse. So what happens when I have a matrix such as A, which is we're applying more than one elementary row operation. So there's several operations that are being applied when we multiply by matrix A. In fact, there are three elementary operations. So before finding an inverse for the matrix A, let's understand what operations are being applied by matrix A. And there are different ways that we could order these operations. So here's one way that we could wind up with matrix A. And that is I can first do a row replacement. I'm going to replace row 2 with row 2 minus 2 times row 3. And let's write out what that matrix would look like. And that would look like E1, I'm going to call this matrix for the first operation, would have row 2 has been replaced with minus 2 times row 3 plus row 2. Next, we could then do an interchange of rows 1 and row 2. So if I interchange these two rows next, then we'll have the top two rows of matrix A. So after applying this replacement, the next thing we can do is an interchange of rows 1 and 2. And that would give us, again, at this point, these top two rows of matrix A would match. And so what is the operation, the matrix that would apply this operation? The elementary matrix for that interchange would be what we get when we interchange rows 1 and row 2 of the identity matrix. So here's the interchange. And then to get the 5 in the entry in the last row, we can do a scaling operation on row 3 by 5. And the elementary matrix for that operation is the matrix that just has top row 1, 0, 0, 0, 1, 0 for the second row, and then the third row gets scaled by a factor of 5. So if I apply E1, then E2, then E3, that's equivalent to doing matrix A. So matrix A is the product of these three matrices in this order. So again, E1 is the first thing that we would multiply by, then we would apply E2, then we would apply E3. So just with functions, we start on the right, and this is the first operation that's applied. Then I compose it with the next operation, and then the next operation. So now we can check our work to see if this works out. So E1 times is this matrix over here. E2 was the elementary matrix for just that single operation of interchanging rows. And then E3 was this scaling operation. And if you multiply this product out, and there are different ways that you might decide to do so, you can multiply these two matrices first and then multiply by the third one. For example, it's a good exercise to practice your matrix multiplication and verify that we do indeed get matrix A back. So we can think about matrix A as a matrix which is a product of three elementary matrices because we've done three different row operations to the identity matrix to wind up with matrix A. So if I want to find the inverse of matrix A, let's use this idea over here. Namely, I'm going to take the inverse of each of these matrices and then reverse the order that we take their product. So in other words, A inverse, by the previous properties that we've proven, A inverse is going to equal the product that I would get if I first do the inverse of E3, so that is furthest on the right, then I multiply on the left by the inverse of E2, and then lastly I multiply on the left by the inverse of E1. So now we're first doing E3 inverse, then E2 inverse, then E1 inverse, and that's going to undo each of these operations in turn, and matrix A and A inverse are going to undo each other. So let's identify each of these inverses. So E1 inverse, remember E1 was this elementary row operation that I replaced row 2 with minus 2 times row 3. And we discussed this earlier in an earlier example, that the inverse of that operation of subtracting 2 times row 3 would be adding 2 times row 3. The inverse operation for interchanging rows 1 and 2 would be to do that same operation again. So the E2's inverse is itself, since applying an interchange 2 times would undo that first interchange. And then lastly, E3 inverse, we had E3 was this scaling by 5. Rather than multiply row 3 by 5, the inverse would be to divide row 3 by 5. So these are the inverses of each of the elementary matrices, and I am taking the product in the reverse order, and the result I get in the end is that A inverse is equal to a 3 by 3 matrix where the top row is 0, 1, 0. The second row is 1, 0, 2/5, and the third row is 0, 0, 1/5. And certainly, as we're learning matrix multiplication, practicing it, I think that it would be a good idea to check these products. Is it true that if I take A that I'm writing out over here, and I multiply it by A inverse, that was a 2/5, and we have 0, 0, 1/5, that if I take the product of these two 3 by 3 matrices, you want to verify that indeed you do get the identity back, and that also when you take the product in the reverse order, so if I take A inverse on the left, and I multiply on the right by A, that this also gives us the identity. So you want to check that multiplying them in both orders gives us the identity matrix back, and it does. So this process works out, okay? If I can identify that matrix A is a product of a bunch of elementary matrices, then I can find the inverse of each of those elementary matrices and then reverse the order that I take their product, and voila, I've got an inverse matrix. So let's try and generalize this process and set up a nice algorithm for doing this in general.